Hello, my name is Jordan Marcincavage, EDM Applications Engineering Team Leader here at Makino Mason. Today we're going to talk about the BX3, which is a fast hole EDM primarily used to machine film cooling features in Aero Engine components. After the presentation, we'll open it up for a live Q&A. If you have any questions during the presentation, feel free to use the chat window. With turbine engine manufacturers focusing on improved engine performance and fuel efficiency, new component designs require the use of more complex film cooling features than ever before. And these new features have varying shapes and vectors. So with the increased amount in different machining vectors, it's important to use a machine with single point tooling. So this would be a machine that's using a tool that has a single point of machining contact like an end mill, rather than what's been historically used before for some of these features, which would be a comb electrode, attacking multiple features at the same vector with multiple machining points. More holes requires higher process efficiency, so you need less setups, less scrap, and faster cycle times. The BX3 is used for small hole and diffuser drilling for high part production volumes of the aerospace and power generation industry. Individual turbine or turbofan engine components are typically referred to as blade or vane details. The blade and vane components are commonly cast details that contain inner hollow features for cooling and weight-saving purposes. EDM drilling is used to create these film cooling features in the blade and vane section. So as you can see on the screen, on the left side we have an example of a blade, and you can see the cross-section with the internal cavities. And then on the right side is an example of a doublet vane, once again cross-section to be able to see the internal cavities. And whenever we talk about film cooling features, we're talking about some of the features that are on the airfoil, so diffusers and holes. So here you can see on the vane and on the blade. EDM drilled cooling holes break into internal cavities, and it's very important to control the machining depth and to not backstrike the opposing wall of the internal cavity. Backstriking can disrupt airflow and the cooling efficiency of the component, and also the part integrity itself can be compromised. So it's very important for whatever machine you're using to have some sort of breakthrough detection to eliminate these backstrikes. Cooling holes can be simple round holes or special shaped holes called diffusers. And the diffuser shapes can vary in design. They can be tapered cones or rectangles or some other shape that basically funnel down into a final through hole. The diffusers are produced to modify or control the airflow and cooling of the component. So what that means is, so on a part like this, air will come in through the back side of the part and it comes out of the diffuser. So the primary function of the diffuser is to help direct airflow where it needs to go for the most efficient cooling. The machine specifications for the X and Y stroke, it's 370 millimeters by 270 millimeters. For the Z axes, we have 750 millimeters of travel. This is the axis that holds the electrode. W axis is 450 millimeters, and this is the axis that holds the positioning guide for the electrode. Each machine comes with a tilt rotary table, and for this we're using an MMK 20 kg table. For the A axis, which is the rotation axis, is 0 to 360 degrees. B axis, which is our tilt, plus or minus 140 degrees. And this lets us attack about any machining vector that we would need. Also on the table we use an Aero or 3R chuck. Aero is the more commonly used. For the electrode diameter ranges for this machine, we can do 0.2 up to 3 millimeter electrodes and anything in between. For max electrode length, 700 millimeters. So with that nice long Z-axis stroke, it lets us hold this longer electrode, which in turn allows for less electrodes required to machine the part, so which means less ATs, less non-cut time. For the C-axis rotation or the spindle, we're up to 1,000 RPMs, and this is fully programmable on a feature-to-feature basis or by electrode diameter. And we're always rotating the electrode during machining, and this really helps to create even electrode wear and also to help improve the concentricity of the hole. For through spindle flush pressure, we're up to 17 MPa. So during machining, we're always flowing water, dielectric, down through the electrode. And this helps with debris evacuation, which can help with increased machining speeds and also quality of the feature. For the work tank, we have a programmable 3-sided rise and fall work tank, and this allows us to perform our submerged machining. The machine also has a 24-station ATC carousel, and this is where we hold our electrodes. So you can either load this with different diameters of tooling to get through your process, or it can be loaded with redundant tooling to reduce operator intervention. The machine also has an 8-station AGC, which holds the electrode guides. For the dielectric fluid on this machine, we're using deionized water, which helps us really get that nice fast machining speed. For the dielectric unit, we have onboard filtration and DI resin systems that are digitally integrated and monitored by the Hyper-I control. We also have a standard chiller that synchronizes and maintains the water temperature to the machine cast structure. So with this, if you see on the left side, you can see the conductivity meter, currently around 15.2. Whenever the machine sees the conductivity go up beyond a certain threshold, it'll automatically allow water to pass through the resin tanks and bring the conductivity back down. We're also always monitoring filter pressure. So this is the back pressure. So whenever we're in the green, the filters are good. Once we get up into the yellow, we'll throw out a warning that informs the operator that it's about time to change the filters. And then once it gets into the red, the machine will alarm out and filters need to be changed. So as you can see in the picture on the right, which is just a representation of the machine casting, we use the casting as a holding tank for water. And since the water is always moving through the chiller, which follows the ambient temperature of your facility, it really helps control any machine movement that may affect accuracy. The machine also has a rise and fall work tank, which allows us to perform fully submerged machining across various workpiece sizes. It also still allows access to the work zone for setup and maintenance type items. And tank positioning is automatically commanded and controlled through model plan, which is our conversational method of programming. The benefits of submerged machining are increased machining speed, improved debris and chip evacuation, stable and consistent machining, improved feature quality and surface integrity, improved breakthrough detection, and also eliminates the need for manual adjustments of auxiliary flushing. So on the screen we have a picture of a comparison of non-submerged versus submerged machining. It's easy to see that the submerged machining has a better recast and less porosity compared to the non-submerged. Multiple vibration control fingers provide support to the electrode to prevent electrode vibration. So since we can use electrodes up to 700 millimeters, and we're always rotating the electrode up to 1,000 RPMs, and the fact that we can go down to as small as 0.2 millimeter electrodes, the vibration control fingers really help keep everything nice and stable. So that's stability during machining, but also stability during ATC or tool changes of small diameter electrodes. One of the biggest quality concerns when machining aero engine components are backstrikes. So whenever we talk about backstrikes, we're talking about drilling through a wall and then making contact with the opposing wall. So backstrikes, they can disrupt airflow and also affect the integrity of the part itself, sometimes making the part scrap. To avoid backstrikes, we use breakthrough detection. And our breakthrough detection uses high frequency adaptive discharge monitoring. And it is reliably detected within 1 second or 1 millimeter of depth at optimum machining speeds. We have various types of breakthrough technologies to accommodate for different types of machining situations, mainly depending on your exit, whether you're drilling your exits normal to the surface, a high angle, or breaking out into a radius. We also have programmable thresholds to optimize the settings on a per feature basis. Many EDM drilling machines control through spindle flush by setting a pressure value. The problem with this is the flow can actually fluctuate or change as the electrode length becomes shorter. And so during machining, our electrode is always eroding away, so the length is always decreasing. So rather than setting a pressure for the through spindle flush, we are controlling the flow, monitoring and maintaining as the electrode length changes. The steady flow helps produce consistent results over the length of the electrode. Monitoring electrode flow adds the ability to check for plugged electrodes. This is done before the machining process, so we can avoid any unnecessary damage to the workpiece. The machine also utilizes a rise-fall ATC. So this is an ATC structure that reduces tool exchange time and eliminates the need to drain the work tank. So as you can see in the picture here on the right, this is our rise-fall ATC. So we have the down position and the up position. Whenever we perform the ATC or the electrode exchange, it's done nice and high, so everything is above the work tank. What this does is it eliminates the need to lower, drain the work tank, raise the work tank and refill it. So it really reduces your non-cut time. Also, the rise and fall ATC system allows for easy access for the operator to exchange electrodes during machining or during the process. So whenever the ATC is in the down position, the operator can easily access and replenish electrodes as needed. There's also a programmable 8-station AGC, which allows for in-process electrode size change for increased flexibility. The machine utilizes an MMK 20 kg tilt rotary table. And as you can see from our diagram, the chuck face sits well below center of rotation. And so what this does is as we're tilting the workpiece through our plus and minus 140 degrees of rotation, the part stays nice and centered around that center. What this does is it reduces the amount of linear movement that's required to access machining features, which in turn reduces cycle time. The machine also utilizes an Aero or 3R chuck, which opens you up for automation possibilities. This table also has the capability of flushing through the chuck, which can help reduce any type of air pockets or cavities that may affect breakthrough detection when drilling into the internal cavities. The machine also has a nice compact design and a small footprint that really helps conserve floor space. All the maintenance is performed at the rear of the machine, which allows the installation of the maximum number of machines at a facility. So as you can see here, we have nice close placement of the machines together. Most of the maintenance access is performed at the back of the machine, as we stated before. And some of the components like the chiller and DI tank have flexible placements to accommodate different factory layouts. And also with the machines nice and close together, it also increases possibility for automation as well. So some of the tooling that's specific to the BX3 are the electrode holder and the guide holder. So as you can see here, the electrode holder is held in the spindle on the Z-axis and obviously holds the electrode. The guide holder is held in the W-axis and holds the positioning guide. So for the electrode guides, we're using anything with a 6mm interface. Electrodes, we're using standard brass tubes, anything from 0.2 up to 3mm, single channel, multi-channel. For collets, we use the ER11, and since this is a water-based machine, normally nickel-plated or stainless collets. There's also an option to add a Renishaw RMP 400 probe to the machine as well. And we use this in our 6-point probing. So 6-point probing measures part alignment error by using the part's 6-point datum structure. So whenever we talk about the 6-point datum structure, we're talking about primaries, secondary, and tertiary on the part itself. And so for this probing, we're using vector probing, which means we can move along a combination of any X, Y, and Z directions. What this means is we don't necessarily have to move in X or in Y or in Z. We can move in compound vectors. So this measuring routine is also an iterative process, which means it's going to be repeated until a specified correlation tolerance is met. And also with our probing, we can either use ball probing or shank probing. So by ball probing, we're just referring to using the sphere or the ball at the end of the probe, which is what's normally used to make contact with the workpiece. But it's also possible to use the shank itself or a point on the OD of the shank. And when you would use this, or when it's the most benefit, is if you have a point that's on a real small or tight radius, like maybe on the leading edge of a workpiece, that's difficult to hit with the sphere itself, we can use the shank. After we're done probing, the linear and angular error found during the measuring is used to compensate the nominal locations. So after we probe the part, we need a way to be able to compensate machining locations. So for this, we use what we call work installation offset, which is our 6-axis compensation method. So like we said before, the 6-point probing can locate the part and determine the part's actual location and orientation. So whenever we say the actual, what we're talking about is the difference between nominal part space, which would be the green shown here, and then the red, which would be the actual. So whenever we program, we're actually programming to the green, but we need to be able to compensate and move the machining locations so it matches the red part. So after we're done probing, we populate the data for the work installation offset used for the 6-axis compensation method. And whenever we talk about that information, we're talking about the information shown here at the bottom of the screen. So that's our X, Y, and Z linear errors, as well as the X, Y, and Z angular errors. The X angle being the deviation about the X axis, the Y angle being about the Y axis, and Z angle being about the Z axis. So with this also we have a total of 32 storage registers, and this helps with parts that have multiple part datum structures, like a vane segment with multiple airfoils. And so the benefit of all this wrapped together with the 6-point probing and the compensation is it allows for simple, cost-effective fixturing. So basically you don't have to fixture or locate using the fixture anymore. So you don't need a gauge quality fixture. You can hold the part in any method that you would like, similar to this, basically just to open up as much access to machining features as possible. The machine also utilizes the Hyper-I control, which is Makino's universal graphical machine interface used across all newer EDM platforms. It has a 24-inch high-def touchscreen, onboard digital manuals and training systems, and also we utilize HyperConnect for interconnectivity and monitoring. So the HyperConnect gives you the ability to view the control from your PC or other device. We also utilize model plan conversational programming, and with this, the model plan project screens, they organize and minimize the operator inputs. Model plan is a programming method that allows the user to create a program by entering key items like tooling, feature, and location information into a tabular format. So it's basically a way to be able to create a program on the machine. So you can also create the program offline using a CAM system and a custom post processor that basically just outputs in the model plan format. Model plan also controls functions like the automatic electrode changes, electrode length tracking, and work tank positioning. So all this is automatically controlled and handled by model plan, so you don't have to take the time to actually program it. For diffuser processing, the use of single point tooling allows us to use CAM to generate NC toolpaths for just about any diffuser geometry. So some examples are shown on the screen, and you can see that they're very similar to like a milling style toolpath. But what makes it a challenge with fast hole EDM is the electrode is always eroding away. So even though we're posting out in X, Y, Z planar moves, we actually need to feed the electrode down in a ramp or a helical motion. And for this, model plan has what we call electrode wear compensation, to where we just tell the machine or tell model plan the anticipated electrode wear, and it will automatically make the ramp for us. Also, the nice thing with this model plan element is we can easily change the diffuser angle and depth by just changing this one value without the need to repost the entire diffuser code. So this is an example of a part that we machined on the BX3. So this is 718 Inconel 3D printed. The basic part size is 2" by 2" by 6". And all the features on this were created using a 0.5mm brass single channel electrode. So 68 diffusers and 48 holes. Had an overall time of around 1 hour, 30 minutes, with 18 minutes of non-cut time, and for machining time or sparking time, about 1 hour and 12 minutes. Now we're going to take a look at a quick video to help visualize some of the items that we discussed. So first we're going to take a look at the basic machine axis convention of the machine. So as we talked about before, the standard X and Y axes. Z and W axes. Z axis holding the electrode, W which holds the positioning guide. So now the tilt rotary table and that big 140 degree plus or minus tilt that we were talking about that helps us access about any machining vector that we need. AGC, so this is where we're loading our electrode guide, and then now we'll grab our electrode. And as you can see, the ATC is in the up or advanced position, so everything we're doing, the ATC up nice and high, so we don't need to lower or drain the work tank. And as we discussed before, breakthrough technology to help prevent backstrikes. The use of 700 millimeter long electrodes, which help us use less electrodes for the machining process and also reduce the number of ATCs. Also the use of the vibration control fingers, which helps us reduce vibration and help with machine stability. The MMK tilt rotary table, where the chuck face is below center of rotation, so the part stays nice and centered around that rotation point. And what this does is it reduces the amount of linear movement that you need to be able to access machining features, once again reducing cycle time. So now for the rise fall ATC. On the left, you can see where the operator can easily replenish electrodes and also access the guide changer, all of this while the machine is running. So now we'll do a brief machine walk around with Jake out on the showroom floor.
Thanks, Jordan. Now I'm going to give you guys a quick overview of the BX3. The BX3 comes equipped with the Hyper Eye, which is standard for all newer Makino EDMs. Also standard with the BX3, we have the 20 kg MMK table. And as you can see, the chuck face sits below the center of rotation, which keeps everything nice and centralized to help reduce linear moves when we are positioning. So we prepared a quick demo program just to kind of demonstrate what the machine can do. All right, to start our demonstration, the first thing that's going to happen is we're going to do a tool change. So currently we are grabbing our positioning guide. So once that is loaded into the W axis, we will go and we will grab our electrode. So as it performs the ATC, when it comes out of here, I want you to pay attention to the whipping of the electrode and how we fix that. So now the electrode is loaded into the spindle, and you can see that the electrode's kind of wobbling back and forth. So once it gets into position here, you'll notice that the rough guide comes down, and the point of that is to stabilize the electrode. And now our stabilizer fingers will close, and the electrode will be pushed through the guide. So now we're just going to demonstrate some of the movements. Tank rising, and again, during an active program, this tank will rise and fall as it needs to keep the guide fully submerged so that we are always doing completely submerged machining. So right now, the through spindle flush is turned on, the spindle is on, and again, this is commanded by flow rate. So if at any time that electrode becomes plugged, we'll throw an alarm. That way no damage is caused to the part due to loss of flush. So right now we got some movements. The tank is currently filling up. And once this is filled up here, we'll demonstrate some other moves. So now the tank is draining. Let's say that you had a feature that was lower on the part, or is the end of your program. Notice that the tank will drain as the tank door falls. So now we're doing some A and B moves, and you can see the full motion of the B. And again, we can go 140 degrees either direction. So now it's positioning as if we were machining some of these features. And again, because of the A and B, we are able to machine in almost any vector. Again, all these retracts, so once you're done with one feature, you move on to the next. We fully program how far we want to retract so that we can minimize those non-cutting moves. So now we're just kind of positioning around the blade so that you can see the movements of the A. And as far as showing the movements of the machine, the ability of the tank door rising and falling, the tank draining, flushing, spindle on, that kind of concludes what we wanted to show you here. So while our program is being ran, I'd like to demonstrate how an operator can come over here. They can inspect or replace a guide and also replenish the electrodes if necessary while the program is being executed. So over here, I can open the carousel door. And if I need to inspect a guide or replace a guide, I have full access to the AGC, and I can pull out the guide, replace it, inspect it, and I'm able to push this back in, close the door, and all that was executed while the program is being ran. So now if I need to replace any electrodes, come back to the control here, and I can lower the carousel. Now this gives me access to the electrodes. So again, I can come over here, open the carousel door, and let's say that I had a spent electrode here. I can undo the clamp, replace the electrode, put it back in the machine, close the door, and when the machine is ready for a new electrode, it'll be ready to grab the replenished electrode. And all that can be done while the machine is in normal operation without interrupting the cycle. So here at the back of the machine, we have the chiller that is on wheels, which makes it easy to move to accommodate your floor space. Also for our resin bottle, this can easily be moved to be more towards the back of the machine, the side of the machine, whatever works for your shop layout. All right, and here we have our pneumatics. You can notice it's easily accessible on the side of the machine here for any maintenance that may need to be done. Here we have our filter tank. So I'm gonna open this up and show you. So these filters are not submerged, and this makes it a lot easier to change out the filters, and it also makes it less messy, right? So I'm gonna close this hood, and right here on the back of the machine, we have a filter drain button. So what this does is when the pump is turned off, this will force air through the filters and get all that water out. So when we're pulling those filters out, we don't have water going all over the floor. This is very convenient. So then if you look at the overall back picture view of this machine, you can easily access the generator cabinet. And also down here we have our high pressure pump and all of our hoses that can easily be accessed to do any necessary maintenance that might need to be done to the machine. So that's all I have for the walk around, and we'll go back to Jordan.
So in conclusion, just to go back over a few of the things that we discussed, we talked about the breakthrough detection and how it helps us avoid backstriking, the dielectric unit, the submerged machining, which helps improve quality and machining speeds, 700 millimeter long electrodes, which helps us reduce the number of ATCs required for a process, flow control that helps us maintain stability over the length of an electrode, probing and compensation, which lets us basically fixture on a part in any way that we want to open up machining access, and also the hyper-eye control. So now we'll open it up for live Q&A to answer any questions that you may have.
All right, so now we'll go ahead and take some questions. All right, so it looks like first question, why do you primarily use brass electrodes? For this, brass electrodes tend to have a higher wear rate, so it makes it easier to control the tip shape. So it makes it easier to reduce pencil tipping and things like that that can affect breakthrough detection. Also, brass electrodes tend to be a little more readily available and cheaper as well. All right. Can other electrode materials be used besides brass? Jake, you want to take this one?
Yeah, so you can use copper electrodes or tungsten carbide, but those we'll really use in like a special cases, such as like for workpiece is carbide. But for the most part, we'll stick to brass.
All right. Why do you use water for dielectrics instead of oil? So the target of this machine is speed, and that's primarily why we use the water. Whereas oil, you get more of a target of surface finish accuracy, but you get the slower machining. So target for this machine is speed, so we use the water. All right. Does the machine have any type of collision detection? So yes, the machine is able to detect collisions between the machine itself and fixture or workpiece, as long as the components are conductive. All right, and we don't see any more questions coming in.
Okay. Thanks, Jordan, for that demonstration. If no one else has any more questions, I just want to remind everyone to stop by and visit us at IMTS on September 9th through the 14th. We will be located in the South Building on level 3, and our booth number is 338519. Looks like we got a few more questions that just came in here, Jordan.
All right. Okay, so what is the diameter range of electrodes that can be used? So for this machine, we're at around 0.2 millimeter electrodes, which is around 8 thou, up to 3 millimeter electrodes, which is around 118 thousandths.
Okay. All right. Looks like that's all we have right now. So like I was saying, stop by and see us at IMTS coming up on September 9th. It's going to be here before we know it. Also wanted to point out, let you guys know what machines we're going to have there in terms of EDM. We will have the BX3 that you saw today. So come by the booth and check it out. Jordan will be there to answer all your questions. We also have an EDAF3 sinker EDM with a tilt rotary table on it, highlighting our AISF rib technology. And then we'll also have a UX3 wire EDM with a FANUC cobot attached to it, showing automation for wire EDM. So come by and see us at IMTS. I want to thank everyone for taking time today and spending it with us. And if you have any questions, don't hesitate to contact your local Makino rep, and we can answer any questions that you have. Thanks a lot. Have a great day.